I want to take you back to the equation for linear approximation. And for that, we needed to have a tangent point. And we're going to show that we have a tangent point at C. So the point of tangency in this case here is that point. And for the y-coordinate, we need f of C. And we also need the slope at that point. So we needed f prime of C. So this equation allows us to find the linear approximation formula, so that tangent line, and we can use that to approximate coordinates. So in this case here, we have this y equals sine x equation, and we need to take that to find the equation of that tangent line. Now I've already gotten it, but we'll just go do it from scratch. So that equation of the tangent line, we're going to make it tangent at 0, 0. Okay, so at x equals 0, y equals 0. And we're going to have to find the slope of that line. So we need to find the f prime of that sine function. So f prime of x. Since that's a sine function, we're going to end up with cosine of x. And then we want the slope at the point of tangency. So we take the cosine of 0, and that's going to give us a slope of 1. So from there, we can write the equation of the tangent line. Y equals our slope. Well, I'm going to start with our y-coordinate is 0 plus the slope is 1 times our x-coordinate of 0.3 that we're going to approximate, and the center, which was at 0. Okay, so there's my equation of my tangent line. I plugged in my x-coordinate of 3. So I'll write this a little bit more formally. So I want the y value on the tangent line at x equals 0.3. And when we calculate this equation, we're going to end up with 0.3 as our linear approximation to that point. So on our graph, we can see that 0.3 is actually very close to the sine graph. And if we use that linear equation, that ends up being just y equals x. We get 0.3 as our approximation. The actual value for sine of 0.3, so the actual value sine of 0.3 works out to approximately 0.295520, and it just kind of keeps on going. Okay, so that's linear approximation. This is something we've done before. Now, why are we revisiting this? Well, it's because if we take a closer look at the linear approximation formula, so we have, this is our linear approximation formula. It looks very much like the first two terms of the Taylor series. So if I look at the Taylor series, p of n of x, our first term is going to be the function evaluated at the center. So f of c, well, that's the same as the y-coordinate of our point of tangency. It's going to be the slope at that same point, so f prime c. Well, we have f prime c as well in our tangent line approximation. And we have x minus c is going to be the distance from the center, x minus c, that represents, so the first two terms of our polynomial expansion, our Taylor series expansions, matches the linear approximation. Now this is not by coincidence. It happens to be that the linear approximation is really just the first, the linear version, approximation version of a Taylor polynomial. We can actually do a quadratic approximation by extending that to the next term. So we can include that next term, and that's going to end up actually being a quadratic approximation to that same curve. So instead of having a straight line approximation, we're going to have a best kind of a tangent quadratic that's going to approximate a point of that curve. And then we can actually just continue doing that. We can take a cubic, we can take a fourth degree, etc. And by taking, we can go to as many degrees as we want. It's kind of hard to imagine, but it's really just linear approximation using better and better curves to approximate the polynomial.